Welcome. I would like to thank everyone for joining us in this session. I am Chih-Mao Chen from Andes Technology, and we have been developing a tool chain for writing vector programs in RISC-V for file. And today, I would like to give a quick tutorial about RISC-V vector programming with C-level Intrinsics. So here are some key features of RISC-V's vector extension. First of all, there's an implementation-defined vector register length, which we call V length here, and the element width in a vector, and the vector length itself can be configured at runtime. And there is also possible to group multiple vector registers together to form a larger vector for better execution efficiency. All vector instructions are defined as polymorphic, which means that it can operate on data types of different widths, and almost all vector instructions in RISC-V can be maskable. It also has a programming model that's agnostic to the vector length. So if you have the same vector binary, you can run it on different vector cores with different VLAN choices. So if you have a vector core, you can write vector instructions in pure assembly, but you probably don't want to do that because the code you want to vectorize may grow very complex. And if there's better intrinsics at C level, you can provide better integration with your other C code. And it's also possible to port existing vector libraries to RISC-V, such as sleeve. But how do you work with the RISC-V scalable vectors? Right now, there's an IFC on RISC-V's GitHub. This is a proposal that defines the C-level vector intrinsics for RISC-V. And this document currently introduces two kinds of interest types, the vector types and the vector mask types. They are both sizeless, since the vector length cannot be determined at compile time. So being sizeless means that you cannot use the size of operator on those, or put these types in a C-level struct or union. On the left-hand side, we have the vector types. They are used to store the data you want to compute with, and it encodes the element type within the vector, which can be, for example, an AB integer or a single position. These are mostly corresponds to the C-level scalar types. The vector type also encodes the LMO, which defines how many vector registers it uses. And the LMO can go from 1 to 8. And if you have the fractional LMO, you write it as F2, which means 1/2 or half of a vector register. On the right-hand side, we also have the vector mask types, which encodes the element width divided by the LMO. This used to be called length in all the standards, but we don't use that anymore. Anyway, length can go from 1 to 4 all the way up to 64. And these mask types are mostly used to as an predication vector in mask operations. Okay, so we also have vector intrinsic functions, which basically maps to one vector instruction, but it's also specialized for a certain combination of element width and LMO. So here we have a vector add between two vectors whose elements are A bits wide. And this is a vector to scalar addition, but the elements are now 32 bits wide. And this slide shows the widening multiplications from single position flows to double position flows. And since this is a widening operation, the LMO is also multiplied by 2 in the return type. So all these types have the same number of elements. Now each vector functions will set up the V type it uses with this special form of V set VOI. This only changes the V type without changing the current vector length. And the compiler can eliminate this extra V set VOI if it says that you have multiple intrinsic codes, but they have the same V type, and it knows that it does not have to keep this extra visible as around. We also made a design choice to make the vector length implicit, so you don't have to pass the vector length around as an argument to these functions, and this function will just use the whatever vector length that was set up by the programmer. And finally, we have a intrinsic function overloading. So since we have a lot of intrinsic functions, and many of them are pretty similar, so if we can infer the types, the V type uses from the argument types alone, then we can overload them with a shorter name. So here we use the first two as an example. They are both vector S, and we can infer that from the second argument to know that if it's a vector to a vector addition or vector to scalar addition, and we can also know the V type. So we can remove the suffix here and overload both of them as V8. So the intrinsic function becomes much easier for the programmers to write. We also have mask vector intrinsic functions, and these functions will take an additional mask and a mask of arguments. And the mask argument indicates which elements are being masked away, and these masked away elements will have its values from the mask of a vector. This is useful if you just want to change a few elements in a vector. So you just provide a vector as a mask of argument, and you don't have to perform a separate V merge to merge the computation vector and the original vector together. Okay, so now this is a array add example from the B array and the C array into A array, and all of these three arrays have are of size n. So if we want to vectorize this loop with streamlining RBV, first of all, we need to know the number of elements we need to process, which in this example is the n. And in the loop computation, we check if we still have the work to do, and if that's true, then in the body we call the VCVL with the element type we want and the desired element, and this VCVL will return the VLO, which is the number of elements we will process in this iteration. And there are two possibilities here. If the number of elements can fill the whole vector register, then it will just return the maximum vector length. But if we are processing the leftover elements, then the VO will just be the n here, and the active vector length will be set to process the remaining n elements. Now we have the VO set up, so we can load the data with a VOE instruction from B and C into VB and BC. Then we use the V add instruction to add the VB and the BC vectors together into VA, and store the VA vector back to the A array with the VSE function. Then finally, we bump the ABC pointers and decrease the n by the number of elements we have done in this iteration, and this completes the streamlining loop. So if we compile the previous program, you will get this assembly, which is very close to what you have written by hand. So you configure the B type, load them, and add the vector together, and set it back to the memory, and bumps the pointer here. So at least we have an NX27V, which is a vector core, and we also have an LVM-based compiler for the core. The compiler has full support for the vector intrinsic, as described in the document, and it also has in the assembly support. The toolchain tracks the latest vector standard, which is 0.9 as of this recording. It can also eliminate the redundant VCVL introduced by the vector intrinsic functions. It can also perform vector register operation for scalable vectors, and even building those vectors into stack and reload them from the stack if necessary. Okay, so that's it. Thank you for joining us, and please let us know if you have any questions. Thank you.